Careful. Careful. There. Just right. Now, nothing could go wrong unless, you know, we had an earthquake or something. Whoa!
Bill Nye the Science Guy. Bill Nye the Science Guy.
Science rules.
Bill Nye the Science Guy.
Inertia is a property of matter.
Bill Nye the Science Guy.
T minus 7 seconds.
Bill Nye the Science Guy.
Brought to you by Richter Beater Shoes. Try a pair of Richter Beaters, and you'll never feel the earth shake again.
Do you realize that every year there are thousands of earthquakes all around the world? Whoa. I guess we just had one. Huh. See, earthquakes happen. When the big pieces of the Earth's crust, the big plates, move a little. You guys okay?
My leg.
All right, stick with it. Sometimes the plates go this way. Sometimes they go that way. Sometimes they go up and down. Doesn't look too bad. Let's check out the rest of the lab. Chase, you okay?
I'm fine. Why?
We just had an earthquake.
Oh, really? Never noticed.
Yeah, the place is a mess, man. You're sure you're okay?
Uh-huh.
All right. I'll tell you what, I'm headed to the pool.
Okay.
You're sure?
I'm fine, Bill.
Okay.
This guy just drives me crazy.
The reason we have earthquakes is because what you might think of as solid rock, the Earth's surface, is really pretty flexible. Like this big foam rubber map of science. Now the Earth's surface is sort of floating on molten or melted rock. The surface of the Earth is floating on molten liquid rock, which is what the center of the Earth is made of. And these foam rubber plates of science in the foam rubber map of the Earth are floating on the liquid water of the pool. Not only is the Earth's surface flexible, but it's broken up into big plates. Huge plates we call tectonic plates. Tectonic plates. Like you can see here, there's something called the Pacific Plate, and all around it are the continents. Now notice that not only are the continents sitting on plates, but so is the ocean. The ocean is sitting on top of something that's floating on top of molten rock. And the boundaries are always slipping and jostling on each other. Slipping, floating, jostling plates. As the plates move, they crack. And the cracks are called faults. Faults.
A fault line.
Now, because the plates are always moving a little bit, the faults can store energy, just like a spring.
A fault line.
With one plate sliding on the other. And when the energy is released, a lot of times you get an earthquake. An earthquake.
The Earth's surface is broken up into plates. Not bad, huh? Oops. Make your own earthquake and see how things get jostled when plates of the Earth's crust rub up against each other. Cut a shoebox in half. Then put the two sides back together so that the cut sides overlap. Then fill the shoebox with sand and pat it down so that it's smooth. Now push the two sides together. And see the little hill you get? That's like the mountains that are formed when plates of the Earth's crust tilt or lift. And when you pull the box apart, you get a rift. But don't take my word for it. Try it. Try it. Try it. Try it.
Scientists measure movement of the Earth's surface with seismometers. It's from old words that mean measuring shaking. Measuring shaking. And here's how they work. Here's a magnet, very strong magnet. See how the paper clip sticks to it? And it's suspended on a point, so it can easily move back and forth. So watch what happens when the surface of the table moves. See, the magnet stays still, and the surface moves this way. It makes an electrical signal in this coil that shows up on this meter. This is how real seismometers work. Real ones, like this one. Now this magnet is right here, and it's hung on these springs. Now this seismometer is set up to measure movement of the Earth's surface this way, this direction, up and down. Now if we take the electrical signal from this seismometer and record it, then we call it a seismograph. Seismograph, writing down the shaking. And here's a seismograph right here. Watch what happens when I move my feet up and down. See, I can make the needle move. Look how much it moves. Just bending my knees, I can make the needle go wild.
Bill.
Oh, sorry. Now back here, we have a whole bunch of seismographs. Look at them, measuring movement of the Earth's surface all over the world. Now these are very accurate and delicate instruments, and scientists know just where they are on the Earth's surface. So by keeping track of where they are and how much they move, scientists can figure out just exactly how the Earth's surface is moving at any time. They're fabulous.
You can make your own seismometer. Get a pencil with an eraser. Cut or rub the eraser all the way down so it's really flat. Get it to stick straight up by sticking it into a piece of clay. Put little plastic bottle caps around the pencil, like this. Take a marble and carefully balance it on top of the pencil, like this. If there's a quake, the marble falls in the direction of where the quake came from. Pretty nifty.
We say cool.
This lava is about 500 years old. That lava, brand new, right out of the oven. We're on a lava field in Hawaii. This is lava. Molten rock. Look at that. Stiff. Thick. And it's hot. I mean, hot. The same kind of rock that's below the Earth's surface. The same kind of rock that the Earth's tectonic plates move around on. Sometimes when energy builds up, plates slip. Slipping, floating, jostling plates. We get earthquakes. Now the movement of the lava around here, molten liquid rock, makes small earthquakes happen all day long. An earthquake party. It's hot! Woo!
Richie, eat your crust.
Mom, how'd they get it to look like there's an earthquake in our old house?
It was special effects, Richie. Now you turn off that TV and eat your crust.
But I don't want to eat my crust.
Son, listen to your mother.
Take a look at this. It's our hot plate rock model of science. And down here is a burner. This stove is like the heat inside the Earth. And the water is like the molten rock, and the wooden plates are like the tectonic or crustal plates on the Earth's surface. See, when rock or air or water or anything is hot, its molecules get farther and farther apart because they're moving faster. They take up more space for how much they weigh, and the cooler rock pushes them up. And that churning makes the plates move. And that's what happens on the Earth's surface, and that's what's happening in this hot rock model of science. When I add a drop of soap, they'll release, and the heat from the stove will make them move. Watch. So they move apart. See that? Isn't that cool? It's the heat of the churning water or the molten rocks that makes the plates move. Ah! 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 Where the plates, the tectonic plates, are spreading apart, that's where we get volcanoes. And where the plates are coming together, that's where we get mountains.
Does your child understand the difference between a discontinuous strike-slip fault and a regional fold system? Well, help has finally arrived. Yes, it's hooked on tectonics, a new easy-to-use learning technique that will have your child understanding earthquakes faster than vertical uplift through a Precambrian gneiss and fibroid granite complex. Order yours today.
See this? Solid rock. But just a few years ago, it was a liquid. This is lava, and it came flowing down this hillside when the small plates that make this the island of Hawaii slid like that, slid like this. Made a lot of small earthquakes, too. We're still getting a lot of small earthquakes around here today.
Here in Hawaii at the Hawaiian Volcano Observatory. This is a station of the U.S. Geological Survey, and we basically studied the volcanoes and the earthquakes that go along with them. These are 3 of the seismic drums where we record a ground shaking that is a continuous vibration caused by magma moving in the eruptive vent. Here, the fault plane is horizontal, and one plate slides over another plate.
Like this.
A normal earthquake is stored up energy that gets released as the ground or the rocks break. The faults are generally vertical, and the movement is like this. Here's Kilauea. We're standing right up here now, and the eruption that we were looking at the vibrations of the ground from is out here. And the part of the volcano that is moving towards the ocean is this entire piece that is sliding out. It's being pushed outward by the magma system. The magma is coming up underneath and then pushes this flank out. This is science.
If an earthquake happens on the other side of the world, how do scientists measure it? Now, please consider the following. See, everyone feels earthquakes. That includes you and me. But scientists not only feel them, we measure them. So take a look at this. Let's say that there's a seismograph, an earthquake detecting station in Jakarta, Indonesia. And they measure a pretty strong earthquake. And they notice that the Earth is moving in this direction. Then a few moments later, a measuring station in New Delhi, India, detects an earthquake moving in this direction. And then a few moments after that, scientists in, say, Cape Town, South Africa, detect an earthquake going in this direction. You'll see, by comparing the direction of all 3 measurements and the time between them, scientists can play a little game of connect the dots. Connect the dots. See? This one would go out this way. Then extend this line and this way. And then extend this one this way. Now, even if the lines don't come together exactly, we know the earthquake was somewhere around here. The epicenter. Epicenter. The epicenter. The center of the earthquake. So scientists can measure earthquakes all around the world just by sitting still. Just like that. Well, thank you for joining me on Consider the following. Go ahead, shake the camera. Earthquake show. Yeah. See? You buying it? It's the earthquake show.
We're members of the California Swiss Search Dog Association, and we're out here training today. Looks like an earthquake just hit out here. So it simulates an actual earthquake that occurred.
Our organization is involved with training dogs for disaster work, mostly earthquake type of things.
Training the dogs to find people that are buried.
You know people are in there, and now you need to find the scent because they're unconscious or they're hurt.
I climbed down in the hole and I pretend to act like a victim in an earthquake.
The dog uses its nose to track the scent, and then they try to find where most of the scent is coming out of the building.
I'm hiding and I have to be quiet, and you just stay as still as possible so the dog has no indication outside of the scent that you're here.
We train the dogs to alert on human scent, which means that they bark or they try and dig and get into where the person is. If you can go in and bring somebody out alive after they've been in there for a few hours or a few days, there's no other feeling like that. So that's what we do with the dogs, is trying to save the people that are in there.
Hey, can you hear me? Good. It seems like we're standing on solid ground. But it's not solid. No, all this whole thing is floating around on molten, melted rock. And that's what makes earthquakes. And earthquakes seem kind of scary. Ooh. But once you understand them, they're kind of cool. I mean, they're part of life. They're science. That's right. I mean, they're just...
You can make your own earthquake kit at home. Here's what you need: bottled water, canned food and can opener, first aid kit, battery-operated radio with fresh batteries, of course, flashlight, and blankets. Do it! Are you doing it? Do it now!
The Richter scale is a way to compare the size of one earthquake to the size of another. Now, the ground can move in all different directions, but to start out with, let's say it's moving up and down, like this. See how we have a nice smooth curve? That's from the ground moving this way. Now let's say we have a bigger earthquake with a bigger ground motion. Let's say we have one 10 times as high. Like this. See how this one is 10 times higher than this one over here? So then the ground would take on a shape something like this. Same nice curved shape, but this stack of chips is 10 times as high as the one over there. But look how many more chips there are. You see, it takes a lot more chips to keep the curve in the same shape. The chips are like the energy in an earthquake. So when the ground moves 10 times as much, it has a lot more energy, about 32 times as much energy. And we have 32 times as many chips. Now, because the numbers can be very small or very large, Richter came up with the idea of using tens. See, let's say we have an earthquake of magnitude 1. Well, it's going to have some ground motion. We'll call it 1. Now let's say we have another earthquake of magnitude 2. Well, its ground motion is going to be 10 times as much. We just add a 0. Then for an earthquake of magnitude 3, we add another 0. So look, an earthquake of magnitude 3 has 100 times the ground motion of an earthquake of magnitude 1. And it has a lot more energy. Now, since Richter came up with this, a lot of other scales have come along. But they all work in about the same way. The bigger the magnitude, the bigger the earthquake. And the bigger the energy there is to knock stuff over. You weren't supposed to see that.
Oh, sorry. New from Faulty Foods, it's Quakin' Oats cereal with a tremor in every bowl.
See this? Seismometer measured an earthquake, probably in Alaska, and it was a big one. Ooh, ooh.
labs report that this trembler is an aftershock from the earlier Northridge quake.
Wow, now there's an aftershock. Just when you thought they were going to stop, and after every earthquake it never fails. People want to know about the Richter scale. How big, what number? Here's my guess and my over or under. 6.0 is pretty strong, I figure. 7.0 is 10 times bigger. This is what happened, so I suppose that's what you get when you're on the West Coast.
This latest aftershock is said to have registered 6.3 on the Richter scale. Scientists at Nye Labs warn that more may be on the way. Science rules.
Well, that's our show. Thanks for watching. If you'll excuse me, I've got some strike-slip shear moduli to investigate.
Produced in association with the National Science Foundation.
That was okay? You convinced? Bavarian chocolate. It's an earth cake. I got a mouthful of dust, sir. So that the mouse way bigger than it has in an earthquake in what? Scientists measure movement of the Earth's surface with seismographs. No, seismometers. Just kidding. Okay. Well, that's our show. Thanks for watching. If you'll excuse me, I've got some strike ship shears, man.